Hi, everybody. My name is Pete Hunt. I'm here to talk to you about what data engineering can learn from front-end engineering. I know that this is a little bit of a funny topic, but bear with me here. So just a little bit about me. I'm from Elementl. We're the company that builds Dagster. We think of Dagster as kind of a next generation Airflow. It's a data orchestrator. But a long time ago in a previous life, I was a founding member of the React.js team, which today is the most popular JavaScript framework and is used by millions of front-end engineers around the world. So I'm a veteran of the JavaScript wars of around 2013 or so. And it was a very exciting time, full of change, and it really set up the next decade almost or so of web development. And in 2022, I take a look at what's going on in data, and it feels very similar to some of the things that we were working on back in 2013 in front end. So back during the JavaScript wars, it felt like there was a new tool you had to learn every quarter, lots of change, lots of great excitement and new best practices. And in 2021, 2022, in the data world, we're seeing the same thing. There's just a lot of excitement and a lot of change. And so while data and front end they're two very different disciplines with different personas and different objectives, there are similar trends, and I think we can project out some of the things that happened in the front end world and maybe get a glimpse at what might happen in the data world. And so I keep saying this word data, like, what do I actually mean? I'm taking a pretty inclusive approach to this term. So when I say the word data, I really mean the space that data practitioners live in. And I think of a data practitioner as anyone who collects, transforms, or analyzes data. So this includes data engineers, ML engineers, analytics engineers, anyone like that. Definitely a focus on more of the kind of like engineering focused data practitioners rather than the other folks, even though it is a pretty big community under that label. So today I'm going to talk about really three things. The first is the platform shift and what that means. The second is kind of, for lack of a better term, the rise of real engineering. And the third is what data can learn from front end. So I'm going to start with the platform shift. So you, as a data practitioner or as an engineer of any kind, you sit in a stack of technologies and a stack of processes. And above you in your stack are your users or your customers or your dependents. And below you in the stack is your infrastructure. And at your level of the stack are the tools that you use, your best practices, your processes, those sorts of things. And we are always thinking about better ways to do our job, ways to improve processes, new tools we could adopt. And it's important for us to be really thoughtful about how we do that and how we make those decisions. And so one frame that I always use when evaluating whether we need to refresh our best practices or our tools is there a change in the layer of the stack directly above me or below me? So what I mean by that is, are our users changing or otherwise asking for something different? Or is the way that we build, the infrastructure that we sit on top of, is that changing in some fundamental way? And in front-end development, back in 2008, there was a huge change to the infrastructure layer underneath where most web developers or front-end engineers sat. And in 2008 was right around the time that Google Chrome came out. And that started out, back in this era, just to give you some context here, Taylor Swift's Fearless record was like rocketing up the charts. Microsoft Internet Explorer was the most popular browser, and Firefox was a rapidly growing browser. And Chrome was brand new on the scene. And one of its big selling points and reasons why people chose it was because of its performance. And that was enabled by something called V8, which is a JavaScript engine. And V8 was an order of magnitude faster than any other JavaScript engine that came before it. And developers took advantage of that performance. And what ended up happening is V8 gave developers this incredible amount of performance, and they built commensurately more ambitious apps on top of it. And so you see the rise, it kind of, the first kind of ambitious browser-based app, I think, was Gmail that most people used, which came before this. But after this, you saw the rise of Google Docs and Google Sheets and Facebook and, even later on, things like Figma, these incredible applications that were built inside the browser that nobody thought could be done before. And what ended up happening was those pieces of software became very complex. And really two problems emerged that were enabled by this platform shift. The first was that the code bases became really, really large and commensurately difficult to manage. So back in those days, you just wrote JavaScript in a script tag or in a file that was included in a script tag. It was all in one big global namespace. And there weren't a lot of best practices, and there weren't even like classes or modules or anything like that. And so it became very, very difficult to manage these large code bases. The second is even small focused chunks of the code base became extremely complex. So the state of the art back in 2008, 2009 was this library called jQuery. It was incredibly impactful and important, but was very imperative. So when you were building applications, you would have some JavaScript state, and then you would use jQuery to imperatively mutate the DOM, which is the way the browser renders a UI. So it would update the HTML in the page imperatively. And as anybody who's worked with like highly stateful imperative systems knows, when you have a lot of mutation and shared state and synchronizing two chunks of mutable state, the business logic can get really, really complex and really hard to debug and predict what's going to happen. So this was a big problem here. And I think data went through a similar transition a couple of years later. So if you take a look at, if you kind of rewind all the way to 2010, believe it or not, I actually didn't realize that Google Cloud BigQuery was the first cloud data warehouse. That's what I realized anyway. I thought it was Redshift, but Redshift was 2012 and BigQuery was 2010. And so BigQuery was the first cloud data warehouse, and it was really impactful. It was the first time that you could just kind of send your data to a cloud service and turn money into fast queries effectively. You pay as you go. It had a very favorable pricing model for people, and it could query large volumes of data like nothing before it. There were certain open source projects like Presto that came out around that time and stuff, but really BigQuery was the first hosted version. Redshift followed in 2012, and Snowflake was founded in 2014. And so right around 2014, 2015 was when the cloud data warehouse really started to get popular, by my memory anyway. And so if you recall, in the JavaScript world, we had fast runtimes leading to ambitious applications, which led to really complex software. And we started to see that in analytics engineering workloads too. So we got these large, scalable, cost-effective for the most part query engines in BigQuery and Snowflake, and Databricks and stuff like that. Practitioners ended up building more and more ambitious applications and pipelines on top of that. And then the code and queries got way more complex, and we needed tools to manage that complexity. So just like the JavaScript stack had these two problems of large, hard to manage code and complex business logic, there are kind of two analogous problems within the data stack. We went to these 1,000-line SQL queries or more, and SQL didn't really have any tools for large-scale code reuse other than the CTE, basically, in most engines. And connecting your cloud data warehouse to the outside world became pretty complicated. You had to bring in an orchestrator, whether that was a cron job or Python script or something like Airflow or Dagster. Most orchestrators were imperative, and they would have to reconcile the state in the warehouse with the state of the world one way or the other. And this is fundamentally mutative, very imperative, very difficult to reason about. So over time, as the underlying infrastructure got better, it enabled practitioners and front-end engineers to do more complex things. We ended up having to adopt real engineering best practices, taken from all over the software engineering domain in order to handle these problems. So one of the first ones is adopting source control and CI. And I think that this is pretty ubiquitous at this point. But for a long time, practitioners and front-end engineers and different domain-specific engineering disciplines, they were using Dropbox for version control, for example. They weren't using Git. In the front-end world, Git and GitHub are ubiquitously adopted at this point. And with the rise of GitHub Actions and GitHub Apps, there's a really rich ecosystem of CI tools that the front-end community has adopted. So you Git push to master, and it just kind of runs your tests for you and runs your static analysis and pushes to production. It's really, really great. So this has been a great trend that we've seen all over a bunch of different domains in the industry, including configuration management, data engineering, and front-end engineering. The second is a move from copying and pasting code to code reuse. So if you rewind, back in the day in kind of front-end world, we didn't have a lot of tools for code reuse. And I want to just go on a little bit of an aside here. The way I think of software, you can think of it as lines of code. You wouldn't ever really measure lines of code as like a core metric, I don't think, but it's interesting and useful to visualize it that way. I think of lines of code as kind of like fossil fuels, right? It's like cheap and abundant energy enabled modern civilization. It enabled us to feed people. It enabled us to have modern medicine and all these great, wonderful things. But if you use too much of it and you don't pay attention to how it scales and you don't work to kind of like reduce it over time, it can produce a bunch of negative externalities. And so you should think of software the same way. Like you got to write software to do your job. You have to create code. You have to ship stuff. But you need to be thoughtful about how you're reusing the code and how it's scaling over time in terms of complexity and the amount of stuff you have to maintain. And so we have two weapons in software development to deal with this. The first is modularity, and the second is abstraction. So when I think of modules, you could probably write pages and pages of definitions about this, but the way I think about modules is it's a way to, number one, keep your code organized, and number two, reuse your code in multiple places. So you can have multiple different modules. They all depend on the same shared library if they have the same set of utilities they need to use, or the same data set they need to query. So on the front end, we saw the rise of a module system called CommonJS in 2009. And in analytics engineering, DBT models is kind of a swing at modularity in the SQL space, and that came out in 2016. So I don't think it's a coincidence that V8 changed the underlying infrastructure and performance characteristics in such a major way in JavaScript and enabled all this new growth in application complexity. And then CommonJS comes a year later. Similarly, the cloud data warehouse really starts getting adopted widely in 2014, 2015-ish, and then DBT comes along a year later. These are just signs that the ecosystem is growing tools to manage this complexity. Another similarity is that the module systems for both JavaScript and SQL are not native to the language. And so you need a compile step that takes those modules as input and then does a bunch of munging and then spits out valid JavaScript or SQL that the underlying engine can run natively. So in the front end world, that tool is called Webpack, and in analytics engineering, that's DBT. It's worth noting that these compilers are not free. So while they do take away a lot of complexity in many ways, it can add a lot of complexity as well. So first of all, you need to add a compile step. So you don't directly run your code anymore. You have to run a compile step, and then the engine runs the compiled code. That compile step can be slow. And over time, it's a very common trend that these compilers start really slow. Users complain about it, and then they get faster. We saw that in front end where these tools were written in JavaScript, and now they're written in Rust, and they're a lot faster. And we've seen with DBT, it's gotten massively faster over time as more users have used it. And then finally, you need to debug your compiled code, which is harder than debugging the code that you're kind of directly seeing in your editor. So we have to kind of, we've grown tools to help deal with that. The other thing besides modularity is abstraction. So the way I think of this is like taking a piece of code and making it generic and applicable to a bunch of different problems. So this lets you reuse the same bit of code for different fundamental purposes. And it also limits how much of the system you need to hold in your head in order to understand it. So as long as you understand the inputs of the abstraction and what the outputs are supposed to be, you don't have to worry about how the abstraction actually does what it does. You just need to know about the inputs and what the outputs are, as long as everything's working correctly. So in a lot of programming languages, this would, classic abstractions would be functions and classes. And then when you kind of take those, language abstractions and then elevate them to the domain, they become even more powerful. So in front end, we had React components that came out in around 2013. This was taking the JavaScript function and like directly elevating it to the problem of managing UI in the browser. And it became a massive success. And, in data, we're starting to see the rise of these metrics layers, which introduce a higher level of abstraction and reusability in the analytics engineering space. Finally, the last kind of real engineering best practice I want to touch on is text editors and the migration from text editors to IDEs. So just to earn my street cred here, I'm an Emacs person. There's not very many of us left, but that's what I kind of cut my teeth on. And I used Emacs for a long time, but eventually Visual Studio Code won me over. Because life without an IDE really does kind of suck compared to life with an IDE. So what do I mean by that? A lot of times when you're in your text editor and you're trying to work on a project, you've got it open, you got your text editor on the right, open on your monitor, and you see a symbol and you say, hey, where is this thing defined and how does it work? So you have to jump from your text editor into the file system or maybe the GitHub visualizer or whatever, and grep through the code and look for where it's defined. Or maybe you switch buffers in Emacs and you just grep within there. But the point is you're switching out from the source file to a separate search step, and then you look through the search results, and then you jump to the definition. It's a lot of work and mental context switching. The second is, now that you've got the symbol, like what's the documentation for it? How do I use this thing? What are the constraints on it? You have to jump from your editor to the docs. And then finally, like, how do I run my linter, my auto formatter, all these tools where you have to jump from the editor into the command line and back again. And IDE can solve all these problems for you. So you can command click on a symbol and jump right to where it's defined. It can include the documentation in line and autocomplete and give you continuous linting, auto formatting, etc. In the front end world, Visual Studio Code really took over, especially about 5 years ago. In the data world, you see a lot of PyCharm, you see some Visual Studio Code, you see the DBT Cloud IDE. There's just basically this trend towards using more tools that actually understand the code, more so than a plain text editor that just gives you kind of basic syntax highlighting. So that's kind of where we are today. I want to talk a little bit about what data can learn from front end. So it's kind of my view that front end is a couple years early or later on its journey. It's a couple years ahead of data in terms of its transition to these kind of like engineering best practices. The platform shift there hasn't been a platform change as recent as kind of the cloud data warehouse in the front end world. So that's it's matured a little bit more. But I think that both have gone on a similar journey towards these engineering best practices. And I want to talk about a couple future ones that we might see adopted in the data space. So the first one, and I'm going to talk about 5 of them. The first one is a move from imperative code to declarative code via reconciliation. So in many ways, analytics engineering is already drinking the declarative Kool-Aid. We've moved from this world of kind of, in 2010, writing a lot of MapReduce jobs to writing SQL. And SQL is much more declarative than MapReduce. So what do I mean by declarative? Declarative code basically specifies what you want, and then the computer figures out how to do it. So declarative code doesn't really take the form of step-by-step instructions for how to do something. It's just a specification for what you want. So with a SQL query, for example, you just describe, the query you want to run, and the underlying engine figures out which tables to query, which columns to scan, which partitions to scan for those columns, et cetera. You don't really have to think about that stuff step by step. Imperative code, on the other hand, is a step-by-step set of instructions that you have to write. And so while SQL is declarative, there's this other trend that is kind of a specific form of declarative code, which is enabled by reconciliation. And so the idea here is that you've got, state in multiple places. You've got the state of the world and the state of your application. And you want to make a change in the world, based on data in your application. So whether you want to create a report or you want to ingest some data or whatever, you want to basically express your business logic as a desired output state, and then have the framework figure out how to generate those step-by-step instructions to do that, and to take those two states, the desired state of the world and the actual state of the world, and then, converge those two things together. So this is actually a pretty popular trend, not just in front end, but all over the place. So in the front end world, I had mentioned this before, but jQuery was a very imperative way of structuring applications. And then React comes along and says, hey, you're going to express your business logic as a pure function where it takes in some application state and it returns a description of the HTML or DOM nodes that you want to be rendered in the browser. So you don't explicitly update the UI. The mental model is you're rendering from scratch every time. And the underlying framework, takes care of looking at your desired output state of the UI and the current output state of the UI. And then it diffs them together, and then it constructs the manual operations needed to update the browser UI to reflect what you want it to look like. And we see this transition in a number of other places too. So, when we as an industry adopted container orchestration, at a large scale via Kubernetes, Kubernetes has a reconciler built in, at its core. So at its core, you give Kubernetes a set of YAML files that describe the pods you want and the load balancer and auto scaling groups and stuff like that. And Kubernetes takes a look at the current state of the cluster and the desired state of the cluster as expressed in that YAML, diffs them together, and then updates the state of the cluster, creates the pods, scales them up, et cetera, based on what you want to actually be in existence in your infrastructure. And also with kind of managing your cloud configuration and your cloud resources. We went from this world of kind of manually poking at your AWS APIs or even the AWS console and creating VMs or S3 buckets or whatever resources you want in your cloud environment, to using what's called config as code via something like Terraform. And when you run Terraform apply, it takes a look at your configuration as code, and it takes a look at the current state of the infrastructure, it diffs them, and then it mutates it modifies the world until it matches what you want as part of your kind of declaratively specified configuration. So, I'm from Dagster. I share this view of the world. We think that orchestration is going to go this way too. And you see Airflow is taking steps in this direction, and we have been for a while as well. Most orchestration these days is expressed as a series of imperative steps. Do this, do that, and then do this one after the other on a schedule or on some other trigger. We think we're going to move to a world where you kind of declaratively describe both how your data assets are computed, as well as constraints around when they should be computed. So rather than just, thinking of it as like running a pipeline at midnight, you say, hey, I want this particular data set to have a freshness of 30 minutes or less. And having the system via reconciliation, take a look at the current, the current state of your data, of your data assets and the desired state, and then diff those two together, and then run only the operations needed in order to kind of converge the state of the world with your desired state of your data assets. And so we think that this is a trend that's going to continue in orchestration as well as other domains. The second trend that I want to highlight is a move from dynamically typed code to statically typed code. So TypeScript is a superset of JavaScript, and it came out, I think it was in 2012, and there was a competitor to it called Flow, but TypeScript won out. And this is basically a superset of JavaScript that adds static type annotations to it. So if you're familiar with Python and MyPy, it's very similar to that. And this was a pretty big revolution in front end. Just for some context, TypeScript is now one of the most popular programming languages of all time, and the majority of open source projects, the vast majority of open source front end projects are now built in TypeScript. So it's seen absolutely massive adoption, and it brings static type annotations and type inference to JavaScript. And this has a lot of really important benefits to developer productivity and enabling other parts of the stack. So, I had mentioned that we had moved, a lot of the industry has moved to IDEs, but oftentimes the IDEs can't fully deliver on the promise of autocomplete and jump to definition without some sort of static type system that adds those capabilities. So by adopting a static type system like TypeScript, front-end developers got a lot more productive because they got these features like autocomplete and jump to definition. Additionally, it brought inline documentation, which was a nice productivity win. And it also helped developers ship higher quality code because you could run correctness checks continuously in your IDE and on every commit. So you didn't have to deploy your application or run a set of expensive, slow unit tests in order to determine whether your application works. You could run this relatively quick static analysis type checking pass and catch a big category of problems with your application. So this was a huge win in the front end world. So in data, I think that every open source Python library should have MyPy types associated with it. I think your users will be really happy with you. We made this a priority at Dagster. We wrote a blog post about it. To be honest, the tool chain surrounding static typing in Python is it's got a lot of rough edges, and so it does take some work to do this. But I do think that this is a future where we really want to see ubiquitous use of Python static types. And I would really encourage library authors to adopt this. And if you're not a library author and you're just a practitioner trying to do your job, read up on it and configure your IDE to support it and see how it works for you. I think it's I think you'll be pleasantly surprised once your configuration is set up correctly, how much productivity you can unlock. The second is, modeling your assets in software and attaching static types to them can help assess whether or not you have kind of problems in your data pipeline before you even run it. This is just kind of like a high level check here, but it's something that you can do. And finally, this is a little out there, but I keep asking myself, why isn't there a TypeScript equivalent for SQL? So why isn't there a superset of SQL that has type annotations and type information associated with it? And then you can get a full kind of autocomplete editor experience. You have this in some in-browser editors, like the Snowflake editor and BigQuery editor are pretty good, but they're not as good as like a full language server implementation. And so I think it would be really interesting if somebody could build this. And I would suspect that somebody is probably working on this right now. The third trend I want to talk about here is templating to programming languages. So I glossed over a bunch of history in the front end world, but when when React came on the scene, which is kind of when I really started paying attention, while jQuery was the dominant way to build applications and it was very imperative, there was a declarative solution out there that people were using, and it was called AngularJS. And React ended up winning a lot of mindshare over from AngularJS, even though they were both declarative. Even though there were a lot of differences between the systems, but one of the main ones was that Angular required the use of a templating language in order to deliver its functionality, whereas React used the full power of JavaScript, like a real programming language. And what we found was users felt a lot of limitations from being forced to use a templating language, and they ended up wanting to go over and use a full programming language. Which is one of the reasons why, one of the things we heard from early React adopters that were coming from Angular, which was like, yeah, Angular was really, really great. And this templating approach was really great for simple applications. And in fact, it was easier than React for simple applications. But once you hit a certain level of complexity, it actually became really, really hard to deal with. So what do I mean by this? I know I keep harping on this issue of tooling and IDE. I think it's important. There's with a templating language, oftentimes because you're mixing the templating language in with the underlying kind of language, whether it's SQL or HTML, your IDE often has trouble understanding it, and you lose a lot of that functionality that you would otherwise get. Those toolings like the tooling like auto formatters and type checkers and things like that, they don't work out of the box when you kind of slap a template language on top of an existing language. The second thing is that complex tasks can be hard or impossible to do entirely in the templating language. What we saw a lot of times in the front end world was people would build these templates and they would hit a wall where they had to do something that wasn't supported by the templating language. And then they would have to implement that in the programming language, like JavaScript. And then they would have to glue that into the template. And so as anyone ever that was trying to get their job done had to have like two editor windows open. One was like the template and the other one was the JavaScript code backing it. And they would have to constantly switch context and jump between those. The third issue is the verbosity. So even if you can express that complex logic in a templating language, it can be very verbose. And because of that, what we found is that for large front-end applications, large templates became rat's nests, and you would go away from them for a month and come back and you wouldn't know what was going on. And so adopting a real programming language for this brought a lot of benefits. You got the full language and tooling ecosystem, you got a lot of additional expressivity, large-scale code reuse, and you got access to a large hiring pool of people, and you can move engineers around between projects. So what do I think data could learn from front end on this? Well, I think less YAML would be nice. YAML's like it's not really a templating language, but it sort of is. It's a lot of times people are like generating it from code anyway, and you don't get type checking, and it's generally very easy to make typos and mistakes. So I think moving away from YAML to something that's more of a real programming language would be great. If you're familiar with Pulumi on infrastructure automation or the config management side of the house, it brings these types of kind of static typing and a real programming language to the problem of configuration management. And then again, I think that somebody should build a superset of SQL that brings static typing and code reuse as a native feature rather than using a templating language. I hope somebody builds that. The fourth thing I want to highlight here is the move from staging to branching for testing your in progress work. So this is a common thing at many jobs I've worked. There's a Slack channel, and then you mention here, and you say, hey, is anybody using staging 3 right now? I need to deploy to it. This is a problem in a bunch of domains, whether it's backend engineering, front-end engineering, data engineering. You got a set of changes. You can't really test it on your local development environment for whatever reason. You want to push it to a staging environment to emulate production. Companies will have one or maybe a couple staging environments that are shared between members of the team. And so you have to claim it for 3 hours, hope that your work fits into that block, and then any collaboration you have to do fits into that block. And also make sure that nobody, deploys to your staging environment while you're in the middle of development. On the front end world, there's this really innovative company called Vercel, which is a place to host your front end application. And they have a really cool feature called preview deployments, which is you basically, every pull request or branch in GitHub gets its own fresh deployment, and you can push to that, and you get a link to a unique instance, and that lives forever, and you can collaborate on that. And we've built that for Dagster Cloud, so you can kind of get your own, every engineer and every pull request automatically gets a staging deployment that they can go play around with without having to spin up resources for it directly or do anything manual. And we see this outside of the orchestration space too. So Snowflake's got zero copy clones, which really enables this style of development. It's really important that this type of stuff is available in the Cloud Data Warehouse, and Snowflake's had it for a couple of years. And we're even seeing kind of innovative new upstarts like Neon, which is a serverless Postgres dialect, make that available in their open source and commercial offering. So you can just branch your whole production database in a safe and cost efficient way. So this branched deployment model is very, very exciting. So just to recap, you don't have to fight over staging anymore. You can collaborate more easily. You can iterate more quickly, and you can work more safely. So this is, I think, one of those rare silver bullets in software engineering. The last one I want to touch on real quick is just, I think that consolidation is on the horizon. I had mentioned back in the day, there was it seemed like there was a new front-end framework every 5 minutes. There were dozens of them, and everyone felt like you had to relearn everything every quarter. And I feel like there's a lot of new technologies coming out every day in the data space, and it feels very similar. So I think we're going to see some consolidation in this space. It took a couple of years, but eventually React just kind of dominated, and now there's 2 front-end frameworks that people use, React and Vue, and everything else has kind of been relegated. So I think that there's going to be some consolidation over the next couple of years. But anyway, to summarize, I think that data and front end are following similar trajectories. I think that we're going to see a shift to more declarative code. I think we're going to see a shift to more static typing. I think we're going to see more use of richer programming languages rather than templating and configuration languages. I think we're going to see a move to branched environments and more consolidation. And by the way, at Dagster, we share this view of the world, obviously, and we're trying to build towards that future as well. And I'll tweet out these links later. But anyway, I want to say thank you for sitting around and listening to me. And I have a couple minutes to take questions. Gonna pop up. So I got one question that's: assuming infinite time and resources and inspired by, say, the front end world, what would be the one tool you'd build for the data world? I would love to see a typed dialect of SQL with code reuse built into it. I'd love to see something like that, like TypeScript for SQL. Anything else? All right. Well, in that case, thank you, everybody.
Thanks so much, Pete, and thanks everyone for attending.